Hi, and welcome to this video. My name is Alina Koteeva, and I'm the marketing manager for the Smart Mobility and Automotive portfolio at we.CONECT. Today, I'm joined by Shubham Shrivastava, technical expert and lead in 3D perception at Ford. Shubham is speaking at the upcoming Auto.AI USA conference that is taking place in San Francisco from June 28th to 30th. It's good to see you, Shubham. How are you doing?
I'm doing well. Thanks for having me.
So to introduce yourself to our community, could you please tell us a few words about your career in 3D perception and perhaps how you see the field evolving in the coming years?
Yeah, so me personally, I've always been fascinated by computer vision in general. Just the idea that you could teach machines to do the same things as us humans do and do it even better, right? A lot of tasks such as object recognition and understanding pose of objects in the images. I think we do a very poor job at pinpointing where exactly those objects are, what is the pose of it, how what the 3D structure of something looks like. I remember back in 2015 when I was looking at this benchmark called ImageNet that was introduced, and a lot of work came around that time that just can take those images as inputs and can tell you what's in the image, and slowly the performance superseded humans' performance at a very short time. And I remember thinking to myself at that time, what if we extrapolate this to the future? What would it look like? So right now, or at that point in time, it could just tell, oh, there is a dog in the image. But going forward, we will be able to not just tell that, but we can tell exactly where the dog is sitting, where it is looking, what the gaze direction of it is, what the whole 3D structure looks like, where is its tail. Even though we cannot see it, we can hallucinate that. And then predict, what the sentiment of that dog might be. All of this is hypothetical. But then just by having that level of information being predicted within the model weights would be fascinating. And look where we have gotten today. We can just take an image with a bunch of objects like cars, pedestrian, and tell its exact 3D pose. We can predict where those objects are going to be in next 10 seconds, what the trajectory would look like. We can pinpoint a lot of the key points around the objects. We can have deformable mesh for pedestrian, things like that. So yeah, just all of this have always been fascinating to me, and I've been passionate about this in general. 3D perception is a natural extension of this. It's just, I've always been pulled towards 3D perception.
I see. It is indeed sounds very fascinating. Yes, and the technology is moving at a crazy pace.
It's going at a crazy pace, yeah. And one of the questions you asked is, how do I see this evolving? In my opinion, this ability for these models to build implicit model of the world into its weights, I think that is something that is going to be really, really critical. And that's a place that I see computer vision going in general. We are going to have foundation models for computer vision, like you're already seeing for large language models. You're seeing GPT-4, PaLM-2, some of those models, right? And us humans already do that. We have built these model of world into our brain. You could perceive things in 3D because of the stereoscopic vision, but we could even do that with our one eye closed. If we close one of the eyes, we can still tell what is where, how far certain things are, what do those objects look like in real world. And the ability for neural networks to do that to just build that implicit model within its weights is something that I see where this field is evolving, and we are already at the ground level of it, where we see things like nerves and diffusion models that can hallucinate what things might look like from a different viewpoint, or in general build a good model of certain objects. So you can just extrapolate that to where we think we are going to be.
Yeah, fascinating, truly fascinating. And so at Ford, could you give us a few examples of how you're implementing the 3D perception right now?
So at Ford, we are building end-to-end perception pipelines, and we are working towards optimizing them for low-cost, low-power chips. As you can already see, perception is a critical system for autonomous vehicles, and some of the classical examples would be trying to detect objects, understanding the lane topology on the roads, traffic signs, traffic lights. All of that is highly, highly important. It's like building part of the brain that is responsible for understanding what the eyes is seeing, and not just building those algorithms, but building them to be efficient enough to be able to run on a highly efficient chip without taking much power and compute.
Mm-hmm. Sounds exciting. So at Auto.AI USA, you're presenting a case study on the current landscape of vision-centric perception and its challenges in autonomy. So in your opinion, what are the most significant challenges that need to be overcome for safe and reliable operation of autonomous vehicles? And then how does vision-centric perception play a role in addressing these challenges?
The way I see these challenges, I think they are threefold. One, the performance gap between camera-based perception or vision-based perception and the methods that depend on all the sensors like camera, radar, LiDAR right now is huge. Second, to be able to deploy these algorithms, these state-of-the-art algorithms on embedded chips is a major roadblock right now, or one of the major challenges. And third, having quantifiable metrics around safety for perception, that is something that is just non-existent. Now, if you look at, for example, Newscene's leaderboard, and if you try to filter it out based on camera and LiDAR plus radar plus camera, you'll see there is a huge difference. Camera-based perception can only achieve up to like 0.6 MAP versus the other perception system can already go up to 0.75 MAP. So that's a huge gap that needs to be filled. There has to be more research to try and push state-of-the-art in vision-centric algorithms so that we fill this gap between 0.6 MAP and 0.75 MAP. Secondly, for metrics, if you see what each of these benchmarks, how each of these benchmarks evaluate the algorithms, they always use some sort of average precision metrics, which takes into account all the objects up to a certain range, regardless of exactly where that object is, exactly what the object is. But if you think from first principles, a pedestrian that is like 10 meters ahead of ego vehicle versus a car that is 200 meters ahead of ego vehicle, you need to put different weights for them inside your metrics. Obviously, you don't ever want to have a false negative in detecting objects that is very, very close to you, especially when it comes to that being pedestrian, bikers, or something like that, versus you could afford to have false negatives for something that is, let's say, 200 or 250 meters away. So having those metrics to quantify how safe your perception algorithm is, that needs to be built. And most of the algorithms today use a combination of LiDAR, radar, and camera. One of the places where cameras can provide certain advantages is in that camera itself offers you highly dense information. No other sensors gives you that. It is cheap, and throughout the years, it has gotten more and more robust. If you also think about it, cameras as a sensor itself is sufficient enough for the car to be able to drive. All the roads, all the signs, everything has been built for humans so that we can just use our eyes as a sensor and we could drive. So from that perspective, camera itself is a sufficient sensor, but it offers you a great advantage when you're trying to do this mix of sensors to be able to drive autonomously on the road.
Mm-hmm. I see. That's really impressive. So you mentioned research, and how do you see the relationship between academic research and then industrial applications in the field of 3D perception evolving in future, and what role does each play in advancing the state of the art?
In my opinion, the divergence between academia research and industrial application is growing larger and larger. Like if you look at all the top tier conferences like CVPR, ICCV, they're all pushing state of the art further and further, and that is great. But if you look deeper into all those papers, they always use big fat GPUs like NVIDIA A100s to do the inference, and they achieve something like 5 to 10 FPS on those. It is never going to be possible for companies like Ford to be able to put those GPUs into production. So I think there has to be more research towards accelerating the algorithm efficiency. Pushing state of the art forward is great, and we have to continue doing that. But a similar level of focus has to be given to the efficiency of some of those algorithms. Like, how do you make those algorithms run faster and more efficient on low cost, low power chips? I think that is the key that I haven't seen too much research in. Simply put, if we cannot put an algorithm into production, it is not very useful for industrial application.
Fantastic. Thank you so much for your time and your insights. Once again, Shubham Shrivastava, technical expert and lead in 3D perception at Ford. He will be joining us as a speaker for the upcoming Auto.AI USA conference that is taking place in San Francisco from June 28th to 30th. Thank you so much, and see you soon.
Thank you. It was a pleasure. See you soon.